So welcome to lecture 4 in Mathematics for Minor Finance. So what we're going to do today is first have a look at wrapping up essentially our treatment of how do we differentiate. In particular, we're going to look at differentiation of exponential and logarithmic functions. So remember that in the previous video we had a look at differentiating power functions and combinations in terms of sums and products and composite functions. Now we sort of add to these last two building blocks, if you wish, the exponential and the logarithmic functions, and we'll see what their derivatives are actually. So after that, we'll go on to use differentiation for the primary use, I guess, that we have for it, which is optimization. So I'll briefly review the notation that we had before already about intervals, and I'll introduce what continuous functions are. And then we'll use that to first have an introduction about what optimization, finding maxima, finding minima, what that means, and then we'll actually have a look at how to actually figure out what the maxima and minima of a particular function are. So that's the program for these lectures. But then in this first part, let's first go to the derivatives of these two kinds of functions, the exponential and the logarithmic functions. So remember, so the exponential function, there's e to the power x, sometimes written as exp of x. And this, we'll actually now see why this e is called a natural exponential function. The reason is it has a particularly natural derivative. So if the exponential function is just e to the x, or if f of x is e to the power x, then the derivative of this exponential function is just itself. So what this says basically is, if you have something which grows exponentially, exponential function, then at each step the size of the growth is proportional to what you already have. So that's basically also the case if you have a bank account with some positive interest rate. So the more you have, the faster it grows, right? Or you have this pond which is growing over with algae. Well, the more you have, the faster the remaining part of the pond is going to grow over. So that sort of makes sense also from what you know about exponentials, but this is what it means in practice. The derivative of the exponential function e to the x is just e to the x itself. How easy can it be? Well, if we know that, then typically we don't just have e to the x, but we have often e to the power something involving x, some other function g of x. So if you remember, this is what we call the composite function, right? We first compute g of x, and then we apply the function e to the power something to that outcome. So we get e to the power g of x. And if you remember the jargon here, g of x we call the interior function, and then e to the power x will be the exterior function in the name giving that we used last video. So we have to use the chain rule if we want to compute the derivatives of this particular function f of x. So what do we need to do? Well, we have to take the derivative of the interior function, so the derivative of this g, what you would do first, g prime obviously for any function, g prime of x. And we have to multiply that by the derivative of the exponential function, which is just itself. So that's e to the power gx itself. So the derivative of e to the power g of x is g prime times e to the power g of x, or you can interchange those freely, of course, e to the gx as you see here, times g prime of x. So let's look at a very simple example. So e to the power x squared. So now this interior function, or the g of x if you wish, is just squaring. So g of x is x squared. So what's its derivative? Well, of course, the derivative of x squared is 2x. So what we get if we take the derivative of this function f x being e to the x squared, the derivative is going to be 2x times e to the x squared. So the g prime x is 2x, and we multiply that by the derivative of the exponential function, which is just itself. Okay? So let's look once more, and we'll do this on paper, of course, at a slightly more complicated example in the sense that this one also involves a product of two functions. So you see the ex squared, e to the power x squared that we just encountered on the previous slide already, but now I'm multiplying this by a power, x to the power 5/3. And then I'm also multiplying this by a constant, which is 6, but that should not worry us too much, I hope. So let's go to paper to see how we would take the derivative of this function k of x. So here we are on paper. So let's rewrite this function k of x. It was given by 6 times x to the power 5/3 times e to the x squared. So you see these two functions essentially which are multiplied together. So the first one times the second one. And so we have a product here, and we can actually apply the product rule that we covered last time to compute the derivative of this function k. So we want to find k prime of x, the derivative of k with respect to x. So what do we have to do? Well, the first part is taking the derivative of the first bit, multiplying that by the second bit. So let's do that. Derivative of the first bit, what do we need to do? We need to take this power here, the 5/3, bring it down, put it in front of the whole expression, also multiplied by 6. So 6 times 5 is 30. This gives us 30/3 times x, and now we have to lower the power here from 5/3 by 1. So it's subtracting 3/3 if you wish. So the remainder is going to be 2/3. So this is the derivative of the first function here, and we have to multiply that by the second function itself. First part of the product rule. Second part of the product rule is take the first function itself, 6 times x to the power 5/3, and multiply that by the derivative of this second part. So what's the second part's derivative? Well, it's this e to the x squared. We actually just saw it on the previous slide, but let's look at this again. So the interior, we need to use the chain rule for that. So the interior function is taking the square, so the derivative of that is 2x. And then we have to multiply that by the derivative of this exponential. That's itself. It's the exponential itself evaluated again at x squared. So this is it, except that we can simplify it a bit, of course. So first of all, let me rewrite 30/3 as just 10, right? 30 divided by 3, that's 10. So we have 10 times x to the 2/3 times e to the power x squared plus 6 times x to the power 5/3. Sorry, let me rewrite this again immediately as well. So 6 times 2 obviously is 12 while we're working on this. X times x to the power 5/3 times x to the power 1 is going to be x to the power 8/3, right? Add the powers. 5/3 plus 3/3, if you wish, is 8/3 times e to the x squared. So this is the first rewriting to make things a bit easier. So this is, in a way, this is fine, except that it's nicer if you already factorize this, because you can recognize actually some common factors here. So e to the x squared obviously appears in both these terms. And actually, we can also take out this x to the power 2/3 from here, so that here goes away entirely, and take it away from the x to the power 8/3. So what would we get? So if I take out those two factors, x to the power 2/3 times e to the power x squared, what we are left with in the first term is the factor of 10. So this first bit gives the first term here. The second bit will be 12 times, well, I took out the e to the x squared. I took out x to the power 2/3, but I have x to the power 8/3, so what's left is x to the power 6/3. Well, 6/3 is 2, of course, so this just changes x squared. Right? So this is k prime of x, the derivative of k of x. So let's go back to the slide. And here on the slide we see the same stuff happening again. in a couple of steps. So the same answers indeed as we arrived at on paper, which is again reassuring. Second part is, well, we looked at the exponential function, the natural exponential function, which has its base e, but we also noticed there are other exponential functions with different bases. Particularly in general, if a is a positive number, we could look at the exponential function a to the power x for any a. So here's an example where a equals 2. So what would be the derivative of the function 2 to the power x? So let me again do this on paper. So how would we deal with 2 to the power x? So we have 2 to the power x, so it's not e to the power x, but 2 to the power x. So what would be the derivative of that? So let's compute the derivative of this function. So how can we do this? Well, the sensible way to do this is to rewrite this 2 to the power x as by saying, well, 2, that's actually e to the power the log of 2, right? That's the same thing as 2. And I'm raising this thing to the power x. But now we can, of course, use that a power or an exponential raised to a power means just is the same as raising the e to the product of those two powers. So x times log 2, same thing, using one of these properties of the exponential function or powers in general. And now we're in business actually, because now we have an exponential function with just base e, of which we know how to take the derivative, because e to the power x log 2 is just e to the power some function of x. So how do we do this again? Well, we take the derivative of what's in this power, so the interior function if you wish. That's just going to be log of 2. So the derivative of x times log 2 is log 2, right? Linear function if you wish. And we multiply this by the derivative of the exponential function with base e, which we know just itself. So it's going to be itself x log 2. So this is fine, we're basically done, except that we might again rewrite e to the power x log 2 as the 2 to the x, which it is equivalent to by going basically in the opposite direction with rewriting stuff. So the final answer here is going to be log 2 times 2 to the power x. So this is going to be the solution to the derivative of 2 to the power x. So let me go back to the slide. So here we're on the slide. We have this 2 to the power x, and here's indeed the answer. It's just postulated here as the right answer, but we just derived this. So more generally, for any a positive a to the power x prime is going to be a to the power x times log a. So you see that fits in with this example where a was 2. The proof is precisely the same, so it's basically what we did with a equals 2, but now for general a. And you should know that, of course, this a really needs to be positive, because here we're taking the log of this a, and remember the domain for the logarithmic function is just positive numbers, so 0 is not allowed, and negative numbers are not allowed either. One other special case is when a equals e. Well, that also works fine, because when a equals e, and we just have e to the power x, so e to the power x here, well, we know the derivative of that should be e to the x itself, and that works because the log of e over here actually is precisely equal to 1, so that fits in with this general rule as well as it should. Okay. So that's the exponential function. So let's then go to the logarithmic functions. It's almost as essentially as simple as this. It's a slight catch here. So the derivative of the log x is actually 1 over x, 1 divided by x. So the derivative of the logarithm of something is 1 divided by that x. So if once we know this, so we're just going to assume that this is true, and you can look up in your book for the proof why this is true. We can actually also, and that's actually what we'll encounter much more in practice, the log of some function of x. In this case, we would like to know what's the derivative of the log of h of x. So here we obviously have to use the chain rule again. So the interior function would be the h of x. The exterior function would be the logarithm. So how do we compute the derivative of that? Well, via the chain rule, we have to multiply the derivative of the interior function, h prime of x. We have to multiply this by the derivative of this log of hx. It's going to be 1 divided by h of x. Because the derivative of the log is just 1 divided what's inside. So let's again do an example, and again I'm going to do this on paper. What's the derivative of this function g of x, where g of x is the log of 4 minus x squared. So let's go to paper. So we have g of x is the natural logarithm of 4 minus x squared. Note actually that this only makes sense if, as long as 4 minus x squared is a positive number, so it should be for x strictly between minus 2 and 2, I'm sure you can see. But let's just put that here actually. The domain of this thing is going to be any number between minus 2 and 2. So let's take the derivative of this function, the prime of x. That is, well, we have to use the chain rule. So the interior function is 4 minus x squared. So what we will do first, compute 4 minus x squared. Or what's the derivative of that? It's obviously minus 2x, right? So the derivative of the interior is minus 2x. I have to multiply that by the derivative of the logarithm, which was 1 divided by what's under the logarithm, 4 minus x squared. So basically this is it. So let's just rewrite this as minus 2x divided by 4 minus x squared. And this is it. This is the result. So we'll see that on paper again. And here we indeed see this. So this derivative of this interior function was minus 2x, as we just noticed. So the derivative of this total function g, this whole composite thing here, is minus 2x divided by 4 minus x. And of course, a different way of writing this is essentially by multiplying both the numerator and the denominator by minus 1. Same thing as 2 times x divided by x squared minus 4. Same thing. So here's an exercise that you might do for yourself, and you'll find the answer to this derivative at the end of the slide pack. So try this and just see whether you can use this, in this case the quotient rule and the derivative of the logarithm to find what the resulting derivative of this function, particular function k, is going to be, and then you can check it at the back of the slides. So that was the final part, if you wish, of these basic derivatives. So the exponential and the logarithmic functions. What we can now do is go on to use these derivatives to optimize functions. So we'll have a look at an introduction into that in the next video.